Hello everyone, I'm Pooria. Today we will delve into the world of heuristics. I'm going to tell you about the challenges we face in understanding their performance, and I'm going to introduce a method that can help you with this process. This is a work that we did as collaboration between USC, Microsoft, and Rice University. As you might have already experienced, finding the absolute best answer can be challenging, computationally expensive, and sometimes impractical at scale. So we use heuristics that help us achieve speed and scale by approximating these solutions. Heuristics are great, we use them in many domains, but at the end of the day, we should remember that there are risks involved in the fact that they can be suboptimal. For example, we find a heuristic in a hyperscaler's traffic engineering system has some corner cases and can be up to 30% less efficient than optimal in these scenarios. So this heuristic is used in the context of traffic engineering, or TE. Here you can see an abstract wide area network that connects different users. These users have some demands and want to send traffic at a specific rate toward the destination. Traffic engineering can have different objectives. Let's focus on one for now. The optimal here tries to maximize the total rate it can support by globally and jointly routing all the demands. As you might expect, it doesn't scale because we usually have too many demands on the order of millions. So the hyperscaler uses a heuristic that tries to speed up this process by reducing the size of the optimization. It first routes small demands through the shortest path, and then uses the optimization only on the larger demands. The size of the optimization here is much smaller, so it can speed up the process. Remember, this is a production heuristic, so we wanted to quantify the risk, and specifically, we wanted to know how much this heuristic can deviate from the optimal. Today, I'm going to tell you about a tool that helped us automatically find these cases, answer these questions, and more broadly, it can help you find cases where a heuristic performs substantially worse than a baseline. So this baseline can be an optimal. You can find the optimality gap. Or in cases you have multiple options, you can compare two heuristics together. We used it in the context of traffic engineering. We found the 30% gap between the production TE system and the optimal. We used it in the context of VM placement. We find a common placement algorithm, first with decreasing, may use twice more servers than the optimal. We also used it for packet scheduling. Here we compare two heuristic, and we find that the heuristic AIFO can have 6 times higher priority inversion than another heuristic SPPIFO. So for the rest of the talk, I'm going to tell you how we came up with this approach that can automatically detect these corner cases and find the scenarios that the heuristic may underperform. Formally, our tool MetaOpt generates adversarial inputs for a heuristic. These are the inputs that cause a large difference between the optimal and heuristic, and these are the inputs that the heuristic is going to struggle with. To use MetaOpt, you need to specify a description of the optimal, a description of the heuristic, and the rest of the process is done automatically. You can already see that we can replace optimal with any other baseline in order to compare heuristic with that baseline. For now, let's focus on just comparing optimal and heuristic. I'll get back to this later and show you the extensions. To design MetaOpt, we need to answer 3 questions. First, we need to find a way to mathematically model this adversarial generation problem. Then we need to find out how we can solve this model and scale it to practical instances. Finally, I'm going to discuss how we can use MetaOpt in different contexts. We observed that, let's start with the first one. We observed that we can model MetaOpt as a game between multiple agents. We have an adversarial generator that has full control over the input and wants to find the inputs that cause a large gap between optimal and heuristic. Meanwhile, we have 2 agents, optimal and heuristic, that they don't have any control over the inputs. They can just try to find the best solution to these inputs. And these solutions, in turn, control the objective of the adversarial generator. So you can already see that we have here 2 levels of authorities: an adversarial generator that controls the inputs, and 2 optimal and heuristic that control the objective of the adversarial generator. Now let's take a closer look at what optimal and heuristic do internally. Optimal takes some inputs and usually solves an optimization, maximizing some objective given some constraints. Heuristics can have different forms. They can be greedy, conditional, random, and many other types of heuristics. We find that we can model many of these in the language of optimization. So the heuristic also maximizes its objective given its constraints. Now we have all these three agents in the optimization language. So naturally, we can translate the whole problem into a single optimization framework. Here, the objective tries to find the inputs that maximizes the difference between optimal and heuristic, mimicking the behavior of adversarial generator. As constraints, we model the behavior of optimal, taking some inputs, solving the optimization, and returning the solution. We also do the same for heuristic. As you can see, each of these boxes are optimization themselves. We have an outer level for adversarial generator. We have two inner levels for optimal and heuristic. This is what we call a bi-level optimization. We have one or more optimization modeled as constraint inside another optimization. So far, I told you that we can model MetaOpt as a game and as a bi-level optimization. Now let's talk about how we can solve this model and scale it to larger problems. We looked at many different solvers, Gurobi, Z3, and we quickly find that these do not directly support this type of bi-level optimizations. The issue is with these inner levels that make the problem very challenging. So we need to translate this optimization into some form that solvers can support. In other words, we need to somehow remove these inner levels. Let's take one of the inner levels as an example. We apply a well-known technique that we call a rewrite. A rewrite tries to describe the solution to this optimization with only a set of constraints with no objective. And under certain conditions, we can show that the solution to this optimization, the solution to the original optimization is the same as the solution that these constraints describe. So by doing a rewrite, we don't lose anything. Again, this is a well-known technique. If you are interested to know more, you can read the paper or the reference. We find that applying a rewrite manually, so then we replace each of these inner levels with the rewritten version of constraints for both optimal and heuristic. And finally, we have these single-level optimizations that solvers typically support. We find that doing a rewrite manually can be a huge burden and can be very complex, time-consuming. So we do the rewrite automatically inside MetaOpt. Users only need to encode the heuristic. Once you use these generic rewrites, you can find that these rewrites they don't scale because they add too many binary variables to the optimization that control the complexity of the solver. So we have three techniques to speed up this process. We have a customized rewrite specific to the type of problem that MetaOpt supports. We have selective rewrite that we only apply rewrite if necessary and needed. And finally, we partition the problem into smaller subproblems so we can solve them faster and in parallel. For this talk, I'm going to give you the intuition behind customized rewrite. If you are interested to know more details or the rest, you can look at the paper. So MetaOpt usually needs to search over this large input space in order to find a reasonable adversarial input with a large gap. And this space can be really large, which slows down our process. We find that it's sufficient in most cases, to only look at these extreme points that lies in the boundaries. So if we limit our search space only to these cases, the search space is much smaller, and we can achieve a better scalability. In MetaOpt, we encode these as constraints by quantizing the input space inside MetaOpt. And this quantization lays the foundation for a customized rewrite, quantized primal dual in the paper. So the high-level workflow looks like the following. Users formulate the heuristic as an optimization. For this, we have a set of helper functions to simplify the process. Then MetaOpt models this as a bi-level optimization and automatically rewrites it into a single level that solvers can support. For the rewrite, we use customized selective if necessary to make sure the process is efficient. Then we partition it into smaller subproblems that we can solve faster and offload it into multiple instances of existing solvers to run in parallel. MetaOpt is not limited to a specific solver. We currently support both Gurobi, a commodity solver, and Z3, an SMT solver. So now the third question. how we can use MetaOpt. So far, I told you the simplest use case, which is comparing optimal and heuristic. In many cases, we know what our workload looks like. We know the space of inputs that we are interested in. We can encode these with some constraints as an input to MetaOpt. And MetaOpt is going to generate adversarial inputs that belong to these input space that we are interested in. For example, in traffic engineering, we find that these are the demands that are sparse and local. We encode it as constraints, and we find that the 30% gap that I told you still holds with these additional and more realistic constraints. In some cases, we have multiple heuristics. We want to find which one is better for our use cases. MetaOpt can help us find scenarios where one heuristic is significantly better than the other, and vice versa, and can help us make our decision in a better way. The third use case is we can take these adversarial inputs, we can study them, we can find the patterns in these adversarial inputs, and generalize them to broader cases. In two scenarios, we were able to prove guarantees about the performance of heuristics. We proved the tighter approximation ratio for 2D FFT sum based on the adversarial inputs MetaOpt generated. We also proved a new bound on the weighted average delay of SPPIFO, a packet scheduling heuristic. Even more importantly, once we understood the weaknesses in a heuristic's performance, we can apply some workarounds. We can modify the heuristic to improve its gap. So demand pinning was the heuristic that I told you earlier that was deployed in a hyperscaler's key system. We modified this demand pinning and were able to improve its gap by an order of magnitude. We also changed SPPIFO and reduced its weighted average delay by 2.5 times. So far I told you how we design MetaOpt, what are the different use cases. Now I want to show an example of how MetaOpt improved our understanding of these heuristics and led to potential improvement. I'm going to use the demand pinning example. Here the context is that we feed the demand pinning and the optimal to MetaOpt, find adversarial inputs, study the patterns, and now I'm going to tell you what we learned. Just a recap, demand pinning forces small demands to go through the shortest path and only uses the optimization to globally route larger demands. So in the example here, we have a small demand from A to C, and demand pinning is going to force it through the shortest path, the green one. Everything is fine until we have a congestion in either of the two links on the shortest path. In that case, by fixing the routing of the small demands, we are taking away some very important capacity that the optimization could have used in a better way. Maybe there was another path that was longer, but if we used that, we would avoid the congestion. And this gets even worse when the length of the shortest path increases. If, in this case, we are fixing the capacity from too many links, and this means the optimization is going to have a lower total capacity to play with. And so the gap increases. Generally, we find demand pinning has a huge gap when we have many small demands between pairs with large shortest path length. Once we understood this, the next step was very straightforward. We added a new condition to the pinning part of demand pinning. We only force a demand to a shortest path if it's small enough, it's less than or equal a threshold, and it's between pairs with shortest path length less than or equal a distance threshold. This criteria helps us bound the amount of capacity that the pinning part of demand pinning can fix before the optimization kicks in and controls the gap. We evaluated demand pinning on cogent code with 200 nodes and 500 links. Here I'm showing you the adversarial gap MetaOpt discovered for each of them. You can see for both demand pinning and different variants of modified demand pinning with different distance thresholds. Here demand pinning has a gap of 18%. Modified demand pinning can have anything between 8 to 1%. So one thing that I want to emphasize is that this doesn't mean that modified demand pinning is better than demand pinning in every aspect. Modified demand pinning fixes the routing for fewer demands, and therefore it's going to be slower. However, this additional condition that we add adds a knob to the heuristic that operators can use to control the trade-off between performance gap and scalability. MetaOpt can help understand this trade-off and tune the parameters. So finally, where we can use MetaOpt. We can use MetaOpt to study heuristics that we can encode either as a convex optimization or as a feasibility problem, which is a type of optimization with no objective. We use it to study 5 different examples of heuristic across 3 different domains. And these heuristics, these examples cover different types of heuristic. Demand pinning is a conditional heuristic, POP is random, FFD is a greedy heuristic. We also support priority-based and admission-based heuristics. To conclude, MetaOpt is a general and scalable heuristic analyzer. We can use it to find performance gaps between optimal and heuristic. We can also use it to compare 2 heuristics and find cases where one of them is better than the other. We can use MetaOpt to prove bound on the performance of heuristics. Finally, we can use it to understand the weaknesses of heuristics and improve the heuristic in some way. We are actively working on MetaOpt. 2 directions that we are interested in is extending the scope of applicability of MetaOpt and also improving the usability. If you are interested, you can check our webpage. Our code is also public. Thank you for listening. I'm happy to take any questions.